let's move on to a quantum picture. So in the quantum picture, light can act kind of as either a wave or a particle. And the crucial kind of difference in the quantum picture is that you have this quantization of the light. So you could have a single particle or single photon of light. So in this case, we can ask the question of what would happen if a single photon of light interacts with the beam splitter. And in this case, the way that we interpret what happens is that because this particle can't be divided in the same way that like a light wave can be divided, it either has to transmit or reflect. So this photon is going to have some probability big T of transmitting and some probability 1 minus big T of reflecting. And again, you might see a phase on reflecting or a phase on the transmission. So from this picture, we can kind of see how a beam splitter could act as a passive switch for photons. So by a passive switch, I mean the photon is entering into some switch. You can't control which way it's going to go, but it will only go one way or the other way. And one way that beam splitters are used as passive switches is in the application of quantum key exchange, specifically the protocol of BBM92. So the description from the previous slide was a bit incomplete, since one thing that can happen with quantum states is that they can actually be in superpositions. And what this means is that a photon could enter a beam splitter, and it has some when it transmits and reflects, it transmits and reflects into a superposition state where there's basically some probability of measuring that it's transmitted and some probability of measuring that it's reflected. But you don't know whether it's transmitted or reflected until you actually measure it. So here, instead of interpreting kind of the outcomes as some probability T of transmission, it's now the probability T of measuring that the photon has been transmitted. And instead of the probability 1 minus T of reflecting, this is the probability of 1 minus T of measuring that this photon has been reflected. So we can still actually use these transfer matrices to describe what happens to these photons, which can be thought of as qubits, when they enter into beam splitters. So we can think about taking our transfer matrix for the asymmetric phase beam splitter from earlier. So is this 1 over root 2, 1, 1, 1 minus 1. And now the vector that we're multiplying by isn't really the electric field of the light wave, and instead this is going to describe our qubit. And so the components in this vector are going to describe kind of the probabilities that this qubit or photon is entering into one of the entry ports of this beam splitter or the other entry port of the beam splitter. So if we take this transfer matrix expression, we multiply it by this expression for a qubit that only enters into one beam splitter port, what we get out in the end is 1 over root 2, 1, 1, which is a superposition state for a qubit. It means that this qubit has a 50% chance of having transmitted and a 50% chance of having reflected, and you don't know if it transmitted or reflected until you actually measure for the qubit. So if you're familiar with quantum gates, then you might recognize this transfer matrix expression as the Hadamard gate. And this is an important gate for quantum computing that can put qubits into superposition states. And so this is how we can see that a 50-50 beam splitter can act as a Hadamard gate for a certain type of qubit that consists of a photon traveling in one path or another path. This is an important application for quantum computing.